Welcome to Chapter 2. Here's your topics. We've got scientific method, measurement, significant figures called sig figs, and unit analysis, which is just converting between units. We will have a little bit of graphing at the end too. That's a small part of the chapter that's not listed here. Now, first thing we got is the scientific method. The scientific method is just a logical approach to solving problems. You use the scientific method all the time. Anytime you have a problem in your head without even thinking about it, you're probably going through the steps of the scientific method. I always use the example of you lose your car keys. You're leaving to go to school in the morning. First thing you do is you observe that your keys are missing. You develop a question, where are my keys? You start doing some brainstorming, some background research in your head. Okay, I think I might have left them by the door, or I might have left them on my nightstand by my bed, or I might have thrown them on the kitchen table last night as I ran in the house. So you form your hypothesis. Your hypothesis is, I think I left them on the kitchen table. It's a pretty easy experiment to run. You go over to the kitchen table, you check if the keys aren't there. Your data, your analysis is, my hypothesis was wrong. So you draw your conclusion, your hypothesis is wrong, you'd start over and you'd keep going. Obviously that's a very simple problem. Some of the scientific problems that are solved are a lot more complex, and the experiment needs a lot more controls, or a lot more constants and things controlled for, to make sure that the experiment satisfies our conclusion. Our conclusion is acceptable based on our quality experiment. We'll move on. A couple things. Observation. That's anytime you observe something, taste, touch, feel, weigh, measure, use tools, instruments, so data that you gather. Now there's two types of data that we'll talk about, qualitative and quantitative. Qualitative is non-numerical, meaning no numbers. So if I say something is blue, that's the quality of that object. So that's a qualitative piece of information. If I say that a rock weighs 25 grams, I am now quantifying its weight, or sorry, mass of 25 grams. I'm quantifying its mass. So we'd say that that is a quantitative piece of information. Quantity, quantitative, think numbers. If I say my height is 6'3", I am quantitating my height. I am putting a number to it. Versus if I say someone's really tall or really short, that's just a qualitative piece of information. Until I actually put a number to it, it's not quantitative. And you can see the examples listed here. Okay, now parts of an experiment. We got 4 parts we're going to talk about. The control. This is a standard for comparison. A constant is a factor that does not vary in the experiment. There's going to be a lot of them. The independent variable is adjusted by the experimenter. So if you set up an experiment, this is the variable that you intentionally change. The dependent variable is the one that you measure, and you see how does the dependent change when I change the independent. So we're going to talk about a few examples here, so you can always come back, look at this. I think the easiest way to discuss them is through examples. So if I've got time versus temperature here, let's say I run an experiment and I want to know how fast it goes. I want to run a reaction. So I mix 2 chemicals and I time how long it takes them to react with each other. Now what I do after that is I heat them up to a certain temperature. I time their reaction again. I heat them up a little more, time it again. So I'm changing the temperature in this experiment. So in this experiment, temperature will be my independent variable, and what I'm measuring is the time. How long is the reaction taking? So how does time depend on temperature? How is the time affected by the temperature? Now if I'm doing this, my control, I need to have a control. I don't know if the reaction gets faster or slower if I just run it at one random temperature. So I'm going to have a baseline temperature that I use, and that's probably going to be room temperature. So I'll run the first reaction at room temperature, time it, see what its time is. Now if I heat it up, does it go faster? I compare it to my controller, does it go slower than my original one, my control? If I cool it down, faster or slower? Now some constants when I run this experiment. If I change a ton of things and the temperature, I don't know if the temperature affected it or if all the other variables did. So if I do this, the only thing I change in this experiment is my temperature. All the other variables I hold constant. The size of the test tube, the containers that I'm mixing them in, the amount of reactants, the amount of chemicals I'm mixing. Trying to think of other things. Who's timing it each time to make sure they're timing it consistently. I make sure everything else is consistent. The only thing that changes is the temperature. Another one is the length of string versus the time of revolution. If I change the length of the string, how does that affect how long it takes for it to swing across and back? Now if I do this, I obviously want to hold the weight at the bottom of the string constant. I don't want to put a different size weight on and change the length of the string. I won't know which one's affecting my time, if it's the weight or the length of the string. And you'd set one length, a certain length as your control. I'll let you think of which one would be the control, constant, independent, dependent for these last two. So you can do that on your own. The conclusion. After you gather your data, what's your conclusion? What ideas do you, or what did you learn from your data? Did it prove your hypothesis correct? Or sorry, poor choice of words there. Did it support your hypothesis, or did it refute your hypothesis? Did it prove it wrong, or not support it? Theory is a statement or model that explains how a system works or why it works. So it's trying to explain a natural phenomenon. And theories are supported by lots of experiments. Theories can change if new information is presented. But I don't want you to think that a theory is just a really loose idea. In science, a theory is a very well-established idea. So I hear people say, oh, that's just a theory. That's not the case in science. When we say it's a theory, it's our current best explanation that we have with the data. So I've heard people say, oh, evolution is just a theory, the theory of evolution. But it is currently our best idea of how species came about. So don't think that it's just a weak idea. It's a very well established. Lots of data supports it. They're very well established. Okay, now a law. The other common misconception is that people think if a theory is proven, it becomes a law, and that is absolutely incorrect. Theories do not become laws. Theories try to explain why something happens. Laws try to describe, or laws just simply describe what happens. The law of conservation of mass says that matter is not created nor destroyed, but it doesn't say why. It just says that that's what happens. It's not explaining anything. It's just simply stating an observation, what happens consistently in nature. There's a law of gravity that says objects of mass are attracted to each other. That doesn't explain why they are attracted to each other. There's also a theory of gravity that tries to explain why or how gravity works. So the difference between the law and the theory, one says what happens, the other just tries to explain why it happens. Now models. Models are an explanation of how a phenomenon occur and how data or events are related. Now these can be physical, visual, verbal, or mathematical. So you create a model of how something works, how something is structured. So examples here, we have E equals mc squared. That would be a mathematical model of explaining a phenomenon in the universe. You've got a model of the atom. You could build this and have a physical model of it. In these we'll learn a little bit about the history of the atom and later in the next chapter, and you'll see how the models of the atom have changed as we've learned more about the atom. You've all taken biology at this point, or I guess some of you are currently in it. The Krebs cycle, here's a model of how that works, what goes in, what goes out of that process. You got the model of a DNA. So these are all examples of models, math equations, drawings. You could have computer models, simulations. So there's all sorts of different ways you can represent a model.